or improve your computing skills, do it all with BBC Learning Zone. Find out more at bbc.co.uk/Learning Zone.
GCSE Bitesize revision now on BBC Learning Zone, updated and improved with new material to match the new curriculum in chemistry.
Hello and welcome to GCSE Bitesize. This programme will help you with your GCSE Science Chemistry exams. There are other programmes about physics and biology, and they'll all help you towards a grade C in your Double Science Award. There's also a higher tier programme for those of you who want to go further. The best way to revise with Bitesize is to tackle one topic at a time, working through the video in bite-sized chunks. Each programme is full of useful information with sample questions for you to try. And there's more in the GCSE Bitesize books and on the GCSE Bitesize website at www.bbc.co.uk/revision. This foundation chemistry programme is in 3 parts: classifying materials, changing materials, and patterns of chemical behaviour. You can use the timings on the menu and the clock in the corner to get straight to the topic you want to study. First, classifying materials. This section about classifying materials is divided into atomic structure, bonding, and properties of materials. First, atomic structure. All matter is made up of particles. Atoms are the simplest particles in an element. Each element is made up of only one type of atom. Atoms cannot be divided without changing the chemical nature of the substance. So what goes on inside an atom?
A cloud of electrons surrounds a central nucleus. The electrons carry a negative electric charge. But right in the middle, the nucleus is positive because it contains a number of positive particles called protons. Also in the nucleus are neutrons, but they play only a small role in chemistry. Most of chemistry is about what happens outside the nucleus, what happens to the electrons.
So every atom has a dense central nucleus containing positively charged protons and uncharged neutrons. The nucleus is surrounded by a cloud of much smaller negatively charged electrons. The nucleus has nearly all the mass, but takes up less than 1% of the volume. 99% of the space inside the atom is empty. The positive charge on the protons equals the negative charge on the electrons, so overall the atom is neutral. There's a force of attraction between the positive protons and the negative electrons. This holds the electrons in place in the atom as they orbit around the nucleus. Protons and neutrons both have mass. They each have a mass of 1 in atomic mass units. The mass of an electron is so small it can be ignored. All the atoms of one element have the same number of protons. Atoms of different elements have different numbers of protons. The number of protons in an element is called the proton number. This is the atomic structure of lithium on the left and carbon on the right. Lithium has a proton number of 3 because it has 3 protons. Carbon has a proton number of 6 because it has 6 protons. The number of electrons in an atom is the same as the number of protons. So lithium has 3 electrons and carbon has 6 electrons. The number of neutrons in the nucleus of an atom is usually, but not always, the same as the number of protons. So lithium has 3 neutrons and carbon has 6 neutrons. The proton number of an element is also called its atomic number. A carbon atom has 6 protons and a proton number of 6, so its atomic number is also 6. The mass number of an element is the number of protons plus the number of neutrons. Carbon has 6 protons and 6 neutrons, so has a mass number of 6 plus 6 equals 12. That's written C for carbon, with the atomic number, 6, above it, and the mass number, 12, below it. The mass number is usually twice the atomic number. An isotope is a version of the element with a different number of neutrons and protons. Normal carbon has 6 protons and 6 neutrons, giving an atomic mass number of 12. But there's an isotope of carbon found in much smaller quantities, with 6 protons and 8 neutrons, giving it an atomic mass number of 14. Isotopes of the same element have the same number of protons and the same atomic number. However, they have a different number of neutrons, and so have a different mass number. Back to the clip to find out more about electrons.
If it were possible to see an atom using a microscope, this is what one might look like. Squashed flat, the electron cloud would look like a set of rings called shells. 2 electrons are all it takes to fill the inner shell, but the next one out can hold up to 8.
So electrons are arranged around the nucleus in different shells or energy levels. The first shell, nearest to the nucleus, holds up to 2 electrons. If it's 1 electron, it's hydrogen, and if it's 2, it's helium. The second shell can hold up to 8 electrons. It goes from lithium with 1 electron in the second shell, up to neon with 8. The third shell can hold more than 8 electrons, but it sticks at 8, from sodium with 1 electron in the third shell to argon with 8. Electrons get as close to the nucleus as possible and fill the shells from the inner shell outwards. The addition of 1 electron in a shell makes a completely different element. The way elements react with each other depends on the number of electrons in the outer shells. There's more about this in the section on the periodic table in Patterns of Chemical Behaviour. Here's a question about atomic structure. These are the electron arrangements of some elements. Which element has an incorrect electron arrangement? Electrons normally fill their inner shell before the next shell can start filling. That means that element A, with only 1 electron in its inner shell, but 8 in its next shell, is wrong. It should be 2, 8, 2, magnesium. Here's another question about atomic structure. An element has 9 electrons. Give the numbers of electrons that fit into each shell. Another element has 17 electrons. Give the numbers of electrons that fit into each shell. The first part of the question asks about an element with 9 electrons. The first electron shell can only hold a maximum of 2 electrons. That leaves 7 electrons to go into the next shell to give the total of 9. This is fluorine. The next part of the question asked about another element with 17 electrons. Again, the first electron shell can only hold a maximum of 2 electrons. The next shell can hold 8 electrons. That leaves 7 electrons to go into the third shell to give the total of 17. This is chlorine. That's the end of the section on atomic structure. The next section is about bonding, how elements combine with each other. Compounds are formed when elements combine due to a chemical reaction. Compounds are held together by chemical bonds. Once the compound is formed, it's difficult to get back to the original substances. This clip explains the role electrons play in making different types of chemical bonds.
Around 80 years ago, scientists began to realize that an atom is made up of a central nucleus surrounded by electrons, and the electrons are constantly moving. Moving in fixed paths called orbits, a bit like planets going round the sun. It was thought that the electrons control how the atom behaves. The electrons control the chemistry. Atoms were thought to behave differently because they have different numbers of electrons. This theory suggests that atoms are not held together like bricks and mortar. There's no glue. Atoms might collect together because their electron orbits overlap. This is one way the atoms are held together as molecules. Another way is for an electron to be transferred, to jump from one atom to another.
We saw two types of chemical bonding there. Covalent bonding is when atoms share some of the same electrons in their outer shells. Ionic bonding is when electrons transfer from the outer shell of one atom to the outer shell of another. First, more about ionic bonding. When metals bond with non-metals, they form ionic bonds. Let's take the example of sodium chloride, which we're all familiar with as common salt. A molecule of sodium chloride is made up of an atom of the metal sodium and an atom of the gas chlorine. Watch this clip to see what happens during this reaction.
This is sodium, so soft it can be cut with a knife. In seconds, the surface will begin to go grey as it reacts with oxygen in the air. But a vigorous reaction needs extra energy to get going. Heating the sodium up gives its atoms that extra energy and primes them for a reaction with chlorine. This reaction is a little chemical miracle. It turns two poisonous chemical elements into a vital cookery ingredient, sodium chloride, common salt. Zooming in, this is a chlorine atom squashed flat. With only 7 electrons in its outer shell, chlorine atoms are looking for one more electron to become stable. They're not fussy. They'll take it from any atom with an electron to spare. Sodium atoms make a natural partner because in amongst the cloud of electrons surrounding their nucleus, there's one electron sitting all on its own in the outer shell. The sodium atom is only too happy to pass that electron over to the chlorine, leaving the sodium with a positive electric charge, so it becomes a positive sodium ion. Meanwhile, the chlorine becomes a negative ion, and the scene is set for a chemical wedding. Because the bond between sodium and chlorine depends on them being ions, it's called ionic bonding. In practice, pairs of ions like this rarely exist on their own. When they gather together, they arrange themselves so positive ions are packed as closely as possible to the negative ions, and that's what gives salt crystals their regular shape.
In the clip, we saw that sodium and chlorine are both very reactive elements. Sodium is very reactive because its atoms have only one electron in their outer shell. And chlorine is very reactive because its atoms have 7 electrons, one missing from their outer shell. Sodium easily loses 1 electron to chlorine and becomes positively charged, while chlorine easily gains 1 electron from sodium and becomes negatively charged. Charged atoms like these are called ions, and the positive sodium ions and the negative chlorine ions are attracted to each other. That's why it's called ionic bonding. Large numbers of positive and negative ions stick together to form sodium chloride crystals, common salt. Next, covalent bonding, which involves the sharing of electrons.
Carbon is the king of covalent bonding. Look at a single carbon atom, and there are 6 electrons orbiting the nucleus. This means that only half the outer shell is filled. Carbon is some way off achieving stability. It needs 4 electrons from somewhere. But if a group of carbon atoms get together, they can share the electrons in their outer shells. That's covalent bonding. It means each atom feels as if it has a complete outer shell. But it doesn't just work for carbon bonding with other carbon atoms. Hydrogen will also bond covalently with carbon. 4 hydrogen atoms and a carbon atom make 1 molecule of methane, natural gas.
In the clip, we saw how methane is made, but covalent bonding is the basis of a huge range of hydrocarbon compounds. Remember, covalent bonding is the sharing of electrons between atoms, so they all achieve a complete outer shell. Non-metals bond with other non-metals using covalent bonds. Ionic bonding is the transfer of electrons from one atom to another. Metals want to lose electrons, so they form ions and ionic bonds with non-metals that want to gain electrons. Here's a question about atomic bonding. A magnesium atom has 2 electrons in its outer shell. Explain the charge on a magnesium ion when magnesium forms ionic bonds with other elements. A magnesium atom has 2 electrons in its outer shell. When it reacts, it loses both of those electrons. This creates a magnesium ion with a stable outer shell with 8 electrons, and means the resulting magnesium ion has only 10 negative electrons, but 12 positive protons, so it's doubly positive, Mg++. There's more about atomic structures and bonding in the higher tier science programme. That's the end of atomic bonding. This section is about the properties of materials. Understanding the structure of atoms and how they bond together will help you understand the properties of materials. As you watch the next clips, see how the properties of materials are related to their atomic structure.
Well, this gold leaf here might look pretty thin. You can almost see through it, but it's actually 250 atoms thick. We need to look a little closer. Magnified by an electron microscope, these are individual atoms of gold. To help understand these images, scientists use models to represent the relationships between the atoms, the actual structure of the material. But what can they tell us about the properties? Now, I've got a battery here connected to a light bulb. If I close the circuit with this gold bar, if gold conducts electricity, then the bulb should light up. Yeah. By being able to look at gold at an atomic level, we can see that it should be a very good conductor of electricity. Moving around between all atoms are electrons, and there are very many of these freely roaming from atom to atom. When you apply a voltage from a battery, this random movement becomes a general drift, and that's an electrical current. This is the surface of diamond. Magnified 100 million times, we can see the individual carbon atoms that make up its very structure. Again, looking at a model of these atoms can help us to understand something of the properties of this material. With diamond, we see that the electrons are tightly bound between the atoms. These bonds are all extremely tough and are very difficult to break because the atoms are being held so firmly together. That's why diamonds are so hard. Unlike gold and other metals, diamond doesn't have many freely roaming electrons to carry the current, so it doesn't allow electricity to flow. It's called an insulator. Here, the same carbon atoms are now arranged in layers. Not all the bonds between the atoms are strong. Those between the layers are in fact very weak, so some of the electrons are freely moving around. This almost looks like a different material. It is. This is graphite. And of course there's graphite in your pencils as well. Now the movement of electrons means that graphite is a conductor of electricity. We show this with my friendly battery. We connect the pencil through the light bulb to the battery. Light bulb lights up. But the layers of atoms in graphite are not held together very strongly. And it's the fact that these layers can slide over one another easily. It means that graphite's a good lubricant. We've now seen that carbon atoms can arrange themselves in two different ways, making two materials with totally different properties. If we look at the atoms of carbon fibre, we can see that they have the same structure as in graphite. But in a fibre, they've twisted into a spiral shape like a rope to make it stronger. Many thousands of these are then bundled together. When resin is added, it joins and reinforces the fibres into one tremendously strong material.
So we saw that gold is a good conductor of electricity because free-roaming electrons between the atoms flow as an electric current. Gold is also flexible, ductile and malleable because the layered structure allows its atoms to slide over each other. The clip also looked at diamond and graphite. These are the two most commonly known forms, known as allotropes, of carbon. They have very different properties because of their different atomic structures. Diamond is very hard. Its electrons are packed tightly between atoms, forming very strong bonds. Diamond is an electrical insulator. That's because there are no free-roaming electrons to flow as current. Diamond is also an excellent thermal conductor. Graphite is soft. Its electrons are not packed tightly between atoms and do not form very strong bonds. Graphite is an electrical conductor because free-roaming electrons between the layers of graphite can flow as a current. Graphite is also a good lubricant because the layers in its structure can slide over each other. We also saw how materials can be modified and combined to create composite materials. Carbon fibres are strong but flexible. Resin is stiff but breaks easily. Combining the two materials creates a composite material that is both strong and stiff. That's the end of the whole section on classifying materials. This section is about changing materials. It covers useful products from organic sources, useful products from metal ores and rocks, useful products from the air, and changes to the earth and atmosphere. First, useful products from organic sources. Organic means from living things. Organic chemistry is the study of carbon compounds. This includes everything that is living or was once living. Compounds made from only carbon and hydrogen are called hydrocarbons. In nature, there are millions of organic compounds. That's because carbon atoms can form strong covalent bonds with each other. They can also join together easily to form chains of different lengths to make many different hydrocarbon compounds. The simplest forms of hydrocarbons are called alkanes. They're all inflammable gases and useful fuels, such as methane, ethane, propane, and butane. All alkanes have a central chain of carbon atoms surrounded by hydrogen atoms. This is methane, CH4, ethane, C2H6, propane, C3H8, butane C4H10, and so on. The burning of alkanes is a most important reaction. During combustion, methane and oxygen give carbon dioxide and water. This reaction is very exothermic. It gives out heat. So many alkanes, like methane, are used as fuel. If there's too little oxygen, then incomplete combustion takes place, giving carbon, soot, and poisonous carbon monoxide, as well as carbon dioxide. All hydrocarbons burn well to produce carbon dioxide and water. Some of the most useful hydrocarbons can be found in fossil fuels, like coal, gas or oil from under the ground. It's a hugely important industrial process to separate crude oil into the many useful different hydrocarbon products it contains. As you watch the next clip, note down some of the different hydrocarbons found in crude oil and the processes used to separate them.
Crude oil is a mixture of liquids and gases. These are mainly hydrocarbons, molecules containing only hydrogen and carbon. Much of the oil extracted from the North Sea is transferred by pipeline to Grangemouth, where it's refined on a massive scale. Fractional distillation separates out the useful components. Hot crude oil is fed in at the base of a tall column, which is kept hotter at the bottom than at the top. Fractions like diesel oils, which contain heavy hydrocarbons, tend to stay near the bottom of the tower. Lighter hydrocarbons have lower boiling points, so they vaporize and rise up the tower, where they cool and eventually recondense. The naphtha fraction, which is used for making plastic, is extracted near the top.
So the first process was fractional distillation, in which crude oil is separated into different substances, or fractions. Different fractions have different numbers of carbon atoms. That means they have different boiling points, so they condense off at different places up the fractionating column. The more carbon molecules, the higher the boiling point. Here's a laboratory demonstration of how fractional distillation works.
Crude oil is a liquid. Many hundreds of solids and gases are dissolved in it. When it's heated, vapors are produced which rise up the glass tube and along the connecting tube to the right. The temperature of this vapor is 68 degrees Celsius and steadies there for a few minutes while it's being produced. As the vapor passes along the connecting tube, it's cooled and condensed into a liquid by a jacket of cold water. This liquid, the first fraction, is collected in a test tube. Then the temperature starts to rise again. The vapor in the tube now looks whiter. The temperature steadies at about 113 degrees Celsius. This condensed vapor collects in a second tube. Soon the temperature rises again. More vapor is given off and the temperature settles down at 165 degrees Celsius to produce a third fraction. Finally, at 212 degrees Celsius, a fourth fraction is produced. Each of these fractions are made up of different chemicals. The first fraction burns very easily and is used to make petrol. The second fraction doesn't burn quite as well. Most of this is converted into petrol by another process. The rest is used to make chemicals for plastics and detergents. The third fraction only burns with a wick. It's used to make paraffin and jet engine fuel. The fourth fraction again burns with a wick, but it makes a very sooty flame. This is used to make diesel engine fuels.
Starting at the bottom, where it's hottest, the heaviest fraction with the most carbon atoms and the highest boiling point condenses first. That's diesel oil, used as fuel in diesel engines and in the manufacture of other chemicals. Next up is kerosene or paraffin, used in jet fuel or for heating, and in the manufacture of detergents. Next, naphtha, used to produce plastics. Then petrol, used in cars. And finally, at the top, where it's coolest, the refinery gases come off, including the alkanes like methane and propane, to be used as fuel. The residue left at the bottom goes to make lubricating oil, grease and bitumen for road surfaces, roofing and waterproofing. Here's a selection of questions you might get about fractional distillation. Why can petrol and diesel be separated by fractional distillation? The answer is that they each have different boiling points. Note that for 1 mark the question only asks why and doesn't want an explanation of how fractional distillation works. Here's a variation. How does the number of carbon atoms in a hydrocarbon affect its boiling point? The more carbon atoms a hydrocarbon has, the higher its boiling point. It would also be correct to say that the fewer carbon atoms it has, the lower its boiling point. And again, for 1 mark, the question does not want a big explanation of how fractional distillation works. Here's a more detailed question on the same subject. Crude oil consists of a large number of different compounds. Explain how fractional distillation is used to produce useful compounds from crude oil. In this question, you're expected to write in sentences about fractional distillation. There are 3 marks on offer here, so you need to make at least 3 different points in your answer. A fairly full answer would go something like this. Crude oil evaporates in a fractionating tower. The different hydrocarbon compounds in the crude oil have different boiling points. That means their vapours condense at different temperatures in the tower and can be collected as purer liquids or gases. Each fraction contains hydrocarbons with different numbers of carbon atoms, and each of these has different uses. Note that there's no need to write lots of detail about the fractionating tower itself and all the different products it produces. There's more about the production of useful organic compounds in the higher tier programme. That's the end of useful products from organic sources. Next, how to get useful products from metal ores and rocks. Many useful products can be extracted from the ground by physical separation processes like filtration, evaporation, crystallization and distillation. This clip explains how we get salt from a salt lake using evaporation and crystallization.
This is the Great Salt Lake in Utah, and surprise, surprise, it contains lots of salt. Local industry takes full advantage.
I'm at the Great Salt Lake Mineral Corporation, and their business is salt production on a very large scale.
A section of the lake has been divided into a huge patchwork of ponds, all very shallow. Salt water from the lake is pumped into the ponds down a canal. The pump itself is encrusted with salticles. As the drops of water evaporate, they leave behind tiny amounts of salt, which build up over time. The water is pumped into these huge ponds and left for many months. The sun heats it up, and the water evaporates, leaving behind salt crystal. Under the microscope, you can see this happening. It's called crystallization.
The same thing is happening on these ponds, but on a much larger scale. The sun heats up the water and it starts to evaporate, leaving the salt solution to get stronger and stronger. Eventually, it becomes saturated. The water just can't hold any more salt in the solution, and the salt starts to crystallise out.
Here's a question about separating materials. Someone has mixed some iron filings and copper sulfate powder together. How could you get the copper sulfate back out of the mixture? This is one way of doing it. If you add the mixture of substances to a beaker of water, the copper sulfate dissolves and the iron filings don't. You can then filter out the iron filings or use a magnet. Finally, you evaporate the water to get back the solid copper sulfate crystals. Unreactive metals like gold and silver are found as small particles of the pure metal, and they can be physically separated from other substances. Most metals are too reactive to be found in their pure form. They exist in the Earth's crust combined with other substances as rock ores. Ores are often metal oxides, or compounds that can be changed to oxides, from which the metal needs to be chemically separated and purified. The more reactive the metal, the more difficult it is to extract. There are two common methods of extracting metals from their ores: chemical reduction and electrolysis. First, chemical reduction. Ores found in the Earth's crust are often oxides or compounds which can be changed to oxides. In order to extract the metal in its pure form, it has to be reduced. That means either losing oxygen or gaining electrons. This clip shows how raw iron is extracted from the impure iron oxide by using carbon in a special furnace known as a blast furnace. Look out for the reduction process.
The carbon will react chemically with the iron ore, taking the oxygen out of the iron oxide and leaving crude iron. Air must be blasted in to generate high temperature, and limestone added to combine chemically with clay minerals in the ore. The product, a molten slag, separates from the molten iron and floats on top.
Iron oxide ore, coke and limestone are fed in through the top of the furnace. The coke is ignited and hot air is blasted in from the bottom through the furnace. In principle, the carbon in the coke reduces the iron oxide to give carbon dioxide plus iron, which runs to the bottom of the furnace. In practice, the chemistry is a bit more complicated than that. The limestone is added to remove the impurities as slag. Another way to extract products from metal ores is by electrolysis. This clip shows how aluminium is extracted from aluminium oxide in the form of bauxite.
Bauxite contains aluminium oxide, the raw material for aluminium production. The first thing they have to do is get rid of the impurities which give it that red colour.
The bauxite disappears into a bewildering array of pipes and vessels. Nothing will be seen of it for several days. After 4 days, it emerges, transformed into swirling crystals of aluminium oxide.
But it still needs to be dried.
At 1200 degrees Celsius, all chemically combined water is driven off, leaving a dry white powder, alumina.
Alumina is pure aluminium oxide. Getting shiny metal aluminium out of alumina is difficult and dangerous in the laboratory. So it's easiest to see what's going on first in a demonstration using another white powder. This is lead bromide, and the two black rods are electrodes made from carbon. They're connected to a power pack. The circuit also includes a light bulb. As soon as a current flows, it will glow, but for now it's dark because lead bromide doesn't conduct electricity at room temperature. Alumina is the same, but heat it up, melt it, and everything changes. Now a current starts to flow. Bromine bubbles off at the positive electrode, and near the negative electrode, molten metal sinks to the bottom. Extracting aluminium from alumina is very similar. It just needs a lot more heat and a lot more electricity. The pot line is the heart of the production process. It's a row of electrolytic cells. They call them pots for short. Inside, they keep alumina hot and molten with massive electric currents.
Currently, the pot lines are running at 163,000 amps. In a day, we use enough electricity to power a small town.
All that electricity does two jobs. First, the electric current heats the aluminium oxide. Heating breaks the strong bonds between aluminium and oxygen. That leaves positive aluminium ions and negative oxygen ions floating in the mix. Next, electric charge draws the ions apart and neutralizes them, turning them into aluminium metal and oxygen gas. Here's where the charge comes from: carbon electrodes. 16 cathodes line the bottom of each cell. Up above them hang the anodes, positive electrodes. It's a big job to replace them, but it has to be done often because the anodes get burnt up when the cell's working. Here's what happens. The massive electric current passes between the anodes and the cathodes through molten alumina. The current keeps it hot. To save electricity, they also add a material called cryolite. It brings the melting temperature down from 2000 to 950 Celsius. Alumina is made from positive aluminium ions and negative oxygen ions. When aluminum melts, the ions are free to move. They're no longer stuck together and can go their separate ways. Opposites attract, so the positive aluminium ions get pulled down towards the negative cathode. They pull electrons off the cathode, neutralizing their electric charge. That makes them aluminium atoms, not ions, so they collect on the bottom of the cell as aluminium metal. Meanwhile, the negative oxygen ions get pulled up towards the positive anodes. There, they give up electrons, neutralize their charge and turn into oxygen gas. But not for long. The oxygen reacts immediately with the hot carbon anode to make carbon dioxide gas.
So the heating process first separates aluminium oxide into aluminium and oxide ions. The electrolysis attracts the positive aluminium ions to the negative cathode, where they become atoms of aluminium metal, and the negative oxide ions go to the positive anode to become oxygen gas.
Each one of these cells produces more than a ton of molten aluminium every day. They suck it out with a machine like a giant vacuum cleaner. They skim off impurities called dross. Then they make it into ingots. These ingots are like blocks of chocolate that get shipped out to customers. Customers then remelt the ingots to cast useful products.
Different methods are used to extract metals depending on how reactive they are. The least reactive metals, like gold and silver, occur naturally. More reactive metals can be extracted from their ore by the reduction of their oxides. The most reactive metals need electrolysis to extract them from their ores. That's the end of the section on useful products from metal ores and rocks. The next section is about getting useful products from the air. First, let's check what air is made of. Air is 78% nitrogen, 21% oxygen, and 1% other gases, mainly carbon dioxide and methane. The next clip explains how important nitrogen is and how it can be extracted from the air in the form of ammonia and used as an important fertilizer for plants. Ammonia has 1 nitrogen atom and 3 hydrogen atoms. It's a poisonous gas, but it makes the food we eat.
Plants need raw materials like carbon, nitrogen and phosphorus to build their leaves and flowers. They get those raw materials from the air and from the soil. Good soil means big, strong plants. Today, farmers add chemicals made from ammonia to soil to make it more fertile. So they're called fertilizers. Plants and people need ammonia for its nitrogen because they're made of protein. Close up, a tiny section of protein might look like this. Hydrogen, oxygen, sometimes sulfur, but always nitrogen. All proteins contain nitrogen. The nitrogen in human protein comes from the plants we eat. And across the world, nearly half of that nitrogen came from ammonia. Ammonia is very hard to make, even in small quantities, and the ingredients are dangerous. Nitrogen suffocates, hydrogen burns. This experiment is tricky to get right. On the left, a glass syringe containing a carefully measured amount of nitrogen gas. On the right, another syringe holding precisely 3 times as much hydrogen gas. And waiting between them, ordinary iron wool, with an extraordinary job to do. All that's missing is heat. The gases mix together as they travel back and forth over the hot iron. If it's working, this is where ammonia is created. This is the chemical reaction that should be happening here. 1 unit of nitrogen and 3 of hydrogen turn into 2 units of ammonia. The iron doesn't take part in the reaction, it's a catalyst. It helps the nitrogen and hydrogen bond together. Now it's time to find out if the experiment has worked. This pump sucks the gas out of the tubes through these yellow crystals. If there's ammonia in the apparatus, they'll change colour to blue. It works, this time. But the equation reveals why ammonia is so hard to make. The double arrows mean the reaction goes both ways. It's reversible. Ammonia can turn back into the ingredients. The trick is to make the ammonia faster than it breaks down. This plant makes 800 tons of ammonia every day. That's enough to fertilize 7,000 football fields. It uses a system called the Haber process. The process needs a giant maze of whining machinery and hissing pipes. To make ammonia, they must first make its ingredients, hydrogen and nitrogen. This is where the nitrogen comes from. There's not much to see on the outside, but on the inside, the machinery pressurizes air to separate out nitrogen from all the other gases around us. Inside this tower, the different gases turn into liquids at different temperatures. It's called fractional distillation. Half a kilometre away is a vast furnace. It makes hydrogen from natural gas, methane. Methane has the chemical formula CH4, 1 carbon and 4 hydrogen atoms. They extract the hydrogen by mixing the methane with superheated steam, H2O, at 500 Celsius. The tremendous heat splits up the methane and the water molecules and frees up the hydrogen. What's left over is carbon monoxide. Finally, the nitrogen and hydrogen come side by side down these pipes. The heart of the plant, where ammonia is made. It's called the converter. Just like the experiment in the lab, the converter contains iron for a catalyst, and it's hot. And it's at such high pressure that the metal wall must be made 11 centimeters thick. Outside, enormous steel bolts hold it together. Here's the problem. High pressure and cool temperature would make lots of ammonia, but it would take too long. So they have to heat the reaction up. That makes it go faster, but it also makes the ammonia break down quicker. Somewhere in between, there's an optimum, a temperature and pressure that works best. So the final stage of the plant starts with a compressor. It pressurizes a mixture of nitrogen and hydrogen gas to about 200 times atmospheric pressure. But the compression has another effect. It also forces the temperature of the gases up to about 350 Celsius. That makes the nitrogen and hydrogen gas molecules split up. Inside the converter, a hot iron catalyst is waiting for the nitrogen and hydrogen. They react together at its surface to make ammonia. The reaction also releases heat, keeping the temperature just right for maximum production, about 500 Celsius. But even so, some of the nitrogen and hydrogen is still left over, so the mixture that passes out from the converter isn't pure ammonia. The very last stage chills the mixture's temperature down so that ammonia condenses out as a liquid. It's drained off from the bottom. Meanwhile, the nitrogen and hydrogen float up to the top and get sent round a loop back to the converter.
So, to make ammonia from the air by the Haber process, air is first liquefied under pressure and the nitrogen separated out by fractional distillation. Hydrogen is extracted from methane at high temperature. The nitrogen and hydrogen are combined to make ammonia. This is done at high temperature and pressure with an iron catalyst. That's the end of the section on extracting useful products from air. This section is about changes to the Earth and atmosphere. It covers how the Earth's atmosphere has changed over time and how the carbon cycle helps to maintain the atmospheric composition. It also looks at the sequence of rock formation and weathering. First, how the Earth's atmosphere has changed over time. Watch the next clip and note down the stages in the evolution of our present-day atmosphere.
The Earth's temperature varies between night and day, from one season to another, and from the poles to the equator. But our planet has an average global temperature of about 15 Celsius.
The Earth is kept warm by the gases in the atmosphere. Without them, it would be over 20 degrees below zero, which is far too cold to support life.
We don't know for certain how the early atmosphere evolved, but we can make intelligent guesses based on evidence from rocks and fossils. We think that about 4,600 million years ago, the Earth evolved from a swirling mass of dust and gases, just like Jupiter is today. The early Earth would have been a molten mass of volcanoes and hot magma. We think that its atmosphere would have consisted mainly of carbon dioxide and water, because these are the gases given out by volcanoes today. Levels of oxygen built up very slowly. When there was enough, about 600 million years ago, then life exploded on this planet, and since then the atmosphere has hardly changed at all.
So the early atmosphere was mainly carbon dioxide and water, gases which escaped from volcanoes. Once plant life appeared on the Earth, the level of oxygen built up slowly. Atmospheric nitrogen came from another volcanic gas, ammonia. For the last 600 million years, the Earth's atmosphere has hardly changed. One vital function of the atmosphere is to keep the Earth at a steady temperature. Watch the next clip and see how it works, and the special term we use to describe the process.
The Earth's atmosphere helps it to retain energy which arrives from the sun in the form of electromagnetic waves. Most of these waves have very short wavelengths, like the ultraviolet radiation which gives you a suntan. Some radiation is reflected back into space, but most of it is absorbed by the Earth's surface. This has a warming effect. Like any warm object, the Earth's surface radiates heat. The radiation goes back out towards space, but this time the radiation is of a longer wavelength. It's in the infrared part of the electromagnetic spectrum. This results in a cooling effect, but some of the infrared waves are trapped by certain gases in the atmosphere. This radiation is then re-emitted, and some of it gets back to the Earth's surface, so the atmosphere keeps the Earth's surface warmer than it would be otherwise. This is the greenhouse effect. Overall, the Earth and its atmosphere receive and give off exactly the same amount of radiation, so the Earth stays at a steady temperature. But without the greenhouse effect, this temperature would be much lower. The atmosphere is 78% nitrogen and 21% oxygen. The gases that cause the greenhouse effect are contained in the remaining 1%. The main ones are carbon dioxide, methane, and water vapour. Although the greenhouse gases form a tiny proportion of the atmosphere, they are vital to our survival.
So it's the layer of carbon dioxide in the atmosphere that keeps the Earth at a steady temperature. This is called the greenhouse effect. Next, how the carbon cycle helps to maintain the composition of the atmosphere. The next clip explains the role of the carbon cycle and the important part played by the oceans.
The oceans cover over 2/3 of the Earth's surface, and we now know that they have a major effect on the Earth's climate. They're important because they store heat in the ocean waters and then transport it around the Earth in ocean currents. They also contain large amounts of carbon, both as marine plants and as dissolved carbon dioxide in the water. This interacts with carbon dioxide in the atmosphere, with marine plants that live on the ocean surface, and with sediment at the bottom of the ocean to form part of the very complex carbon cycle.
The level of carbon dioxide in the air depends on many different processes. Photosynthesis uses carbon dioxide as a raw material to produce sugars, so plants take carbon dioxide out of the atmosphere. Both animals and plants get their energy by respiration, a chemical reaction which releases carbon dioxide into the atmosphere. Carbon dioxide dissolves in the ocean, but this is a two-way process. When the sea gets warmer, some of the carbon dioxide comes out of solution and passes back into the atmosphere. Natural processes like these balance out, so that the tiny percentage of carbon dioxide in the air is maintained. But human activity is now increasing carbon dioxide levels.
So the carbon cycle of respiration and photosynthesis among animals and plants maintains a constant level of carbon dioxide in the atmosphere. There's also concern that burning fossil fuels, like coal and petrol, is increasing the amount of carbon dioxide and causing the Earth's temperature to rise. That's global warming. Others say that global warming is just one of the many natural long-term temperature changes that have happened throughout the Earth's history. The next part looks at the sequence of rock formation and weathering that makes up the Earth. There are three types of rock you need to know about. They are igneous, sedimentary, and metamorphic. These rocks are linked to each other by the rock cycle. The next clip explains how it works.
When a volcano erupts, it's the beginning of one part of something known as the rock cycle. Now, there are three types of rock in the Earth: igneous, sedimentary, and metamorphic. Volcanic rock is called igneous rock, and igneous comes from the Greek word meaning fire, and that's where it's coming from.
Molten rock, hotter than fire. But how is it hot? The center of the Earth, the core, is thousands of degrees Celsius. It's hot enough to make molten rock, which is what the next layer, the mantle, is made of. The Earth's skin, or crust, is anything from 5 to 75 kilometers thick. It's cooler, and so it's solid. Sometimes the molten rock pours out through volcanoes.
This is brown sugar in water. When heated, it becomes like toffee. But when I pour it on this tray, it cools and solidifies like molten rock. And this is what happens with igneous rocks. Igneous rocks have a crystal structure, and the size of the crystals depends on how quickly the rock cools. The quicker it cools, the smaller the crystals. Now, once the rock is outside, things begin to change, and this is due to the weather.
Rainwater gets into the cracks and freezes. The ice expands as it forms, and the force is large enough to split the rock.
Eventually, the rock has so many cracks. This has been very well weathered. Easy. But what happens to the bits of rock that break off? Over the years, bits of sedimentary rock settle on the seabed because of gravity, and the layer gets to be very thick. And the thicker the layer gets, the more pressure is exerted on the bottom of it.
As the particles get squashed, the water is squeezed out, leaving deposits that cause a process called cementation, where the particles are cemented together. Over time, the squashing and cementing of the sediment forms sedimentary rock.
Rocks made of sand that have been compacted and cemented are called sandstone, like the walls of my cave. This means that this cave is in an old sea or lake bed. The water disappeared long ago, and the process takes millions of years. So this sandstone is 235 million years old. Washed in with the sand are shells and other organisms, and they get squashed as well to form limestone. And limestone is another sedimentary rock. This is limestone, but this is not the end of the story. After this sedimentary rock's made, the weight of the layers pushes them deep underground, where the earth can heat and squash the sedimentary rock further. Now, when it does this, the rock changes yet again, and this third type of rock is called metamorphic. Both sedimentary and metamorphic rocks can work their way to the surface and be eroded by the weather and make their own rock cycles. The other possibility is that metamorphic rock can get heated and melted down, ready to be thrown out of the earth again to make igneous rocks. So the whole thing starts again. That's why it's called a rock cycle.
So, over millions of years, igneous rocks are eroded and weathered, transported and deposited to become sedimentary rocks, which under heat and pressure can become metamorphic rocks. Metamorphic rocks can either erupt back to the surface as igneous rocks, or be exposed or lifted to the surface by movements of the Earth's crust to complete the cycle. Igneous rocks are the oldest rocks on the Earth. They were first formed when the molten Earth began to cool down and solidify. Examples of igneous rocks are granite and basalt. Sedimentary rocks are younger. They are deposited in layers made from eroded particles of igneous rock and other material. They're changed into solid rock by pressure and heat, compacting and cementing the lower layers. Examples of sedimentary rock are limestone and sandstone. Metamorphic rocks are made from other rocks by great pressure and heat. Examples of metamorphic rock are marble and slate. Here's a question about the rock cycle. Name the process taking place at each of the labelled stages of the rock cycle. Process A is weathering. Process B is transportation. Process C is sedimentation. Process D is cementation, where rocks are forced deep underground. Process E is where rocks erupt again or are pushed to the surface by uplift or folding. That's the end of the whole section on changing materials. This section is about patterns of chemical behaviour. It's divided into the periodic table, chemical reactions, rates of reaction, and energy transfers in reactions. First, the periodic table. The periodic table is a table of all the known elements, organised according to their properties and their atomic structure. The periodic table shows each element by its chemical symbol. Understanding the periodic table and the information it contains will help make chemistry more logical. This next clip explains some of the patterns using a reduced form of the periodic table.
If the elements are arranged in order of atomic number, some interesting patterns can be picked out. For instance, these elements are all gases at room temperature. This property disappears and reappears at intervals. It seems that these properties aren't just mixed up any old way, there's a pattern. Similar patterns can be seen in the chemical properties of the elements. For instance, these elements are all metals. They conduct electricity. And these are non-metals. They don't conduct electricity. And some elements don't fit easily into either category.
The elements are laid out in the periodic table in order of increasing atomic number. The table is arranged in groups, up and down the table, and periods across the table. Each group contains elements that have the same number of electrons in their outer shell. The main groups are numbered from group 1 to group 8, sometimes called group 0, which usually indicates how many electrons there are in the outer shell of all the elements in that group. Thus, all the elements in group 1 have 1 electron in their outer shell, and all the elements in group 2 have 2 electrons in their outer shell, and so on. The periods across the table represent which electron shell is filling up. Shell 1, shell 2, shell 3, and so on. Because they have the same number of electrons in their outer shell, elements in the same group have similar properties. The periodic table helps us understand and predict all kinds of patterns of chemical behaviour. That's because chemical behaviour is related to the arrangement of electrons. Now we'll look at the parts of the periodic table you need to know about. The group 1 alkali metals, the group 7 halogens, and the group 8 noble gases. First, the group 1 alkali metals. Let's look at the pattern of chemical behaviour shown by these group 1 metals: lithium, sodium, potassium, rubidium and cesium. Watch this classic clip and note down how these metals react and think about why this might be.
Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
As you saw, all the alkali metals are very reactive, and their reactivity increases as we go down the group. When added to water, lithium floats and fizzes, giving off hydrogen. Sodium also floats, but skims across the water surface, also fizzing and giving off hydrogen. Potassium floats as well, but so much heat is produced it sets the hydrogen alight. Rubidium reacts very violently, producing sparks and flying fragments. And cesium explodes violently, smashing the glass container. Why are they all so reactive? By their position in group 1 of the periodic table, we know they've all got 1 electron in their outer shell. Lithium has 2 and 1 electrons. Sodium has 2, 8 and 1 electrons. Potassium has 2, 8, 8 and 1 electrons, and so on. In each case, the outer electron is desperate to combine with something else, which is why the alkali metals are so reactive. But why are the metals more reactive as they go down the group? It's because each successive metal has 1 more electron shell, which puts that single outer electron further away from the positive nucleus. That makes the bonding weaker, so the single electron can more easily combine with something else, which makes each element more reactive than the one before. The next group you need to know about is group 7, the halogens. The group 7 halogens is another group of highly reactive elements near the other end of the periodic table. The most common ones are fluorine, chlorine, bromine and iodine. Watch the next clip and see if you can work out why these halogens are so reactive.
In this model, the most reactive elements are shown the tallest. Group 1 elements sit at 1 peak of reactivity, but way across at the far side, elements in another group are just as keen to react. Here is group 7.
If you were to start at fluorine, well, you wouldn't get very far. I mean, that really is the most reactive gas in the periodic table, and indeed it took ages for chemists actually to isolate it because it was so reactive. Suppose that you got round that problem and put yourself in a spacesuit that enabled you to survive. You would actually see a very interesting countryside as you walked down the group. You would see fluorine as this rather delicately pale green, almost colourless gas. Then you go into a region of slightly darker colour, greenish yellow chlorine. Then you come to really a deep brownish red lake, bromine. And then on the other shore of that lake there is purple, violet, black crystals of iodine. It really is a very beautiful walk to take. It's the most colourful part of the periodic kingdom.
Colourful, but highly reactive. Group 7 elements are dangerous to humans. During the First World War, chlorine gas was used as a weapon. It reacted with the water in soldiers' eyes to form bleach and hydrochloric acid. Thousands were blinded. The reason chlorine was such a horrific weapon is locked inside its atoms. 2 electrons are all it takes to fill the inner shell. but the next one out can hold up to 8. In chlorine it's filled, but the third shell isn't. Again, it's got room for 8, but with only 7 spaces occupied, chlorine has a gap which it is desperate to fill, and that's why it is so reactive.
So why are the halogens so reactive? By their position in group 7 of the periodic table, we know they've all got 7 electrons in their outer shell. Fluorine has 2 and 7 electrons. Chlorine has 2, 8 and 7 electrons. Bromine has 2, 8, 18 and 7 electrons, and so on. In each case, that one missing outer electron makes each halogen desperate to combine with something else, which is why they're so reactive. But why do the halogens get less reactive as they go down the group? It's because each successive halogen has one more electron shell, which puts the gap for a missing outer electron further away from the positive nucleus. The further away, the weaker the bonding, so it's more difficult to attract an electron from another atom to fill the gap. The last group in the periodic table you need to know about is the group 8 noble gases, sometimes called group 0. The group 8 noble gases are all at the extreme right-hand end of the periodic table and include helium, neon, argon, krypton and xenon. How do you expect them to react with other elements?
The goal of every element is to fill its outer shell of electrons. But one group of elements has already got there, group 8, on the far right of the periodic table.
Really, there's not much to see here, and very little going on. These are the so-called noble gases. Right at the bottom we have radon. Not much is known about radon, except that it's intensely radioactive, which is why people don't like to investigate its properties. A bit further up you get to gases like xenon and krypton, argon and neon. These are gases that are used in, well, advertising signs and in lasers and so on. But they were once called the inert gases because chemists, when they were first discovered, thought that they simply didn't react at all.
Now we know that's not always true. But the group 8 gases still hide away in the periodic table because they're so unreactive.
So by their position in group 8 of the periodic table, we know that each of the noble gases has a full outer shell of electrons. Helium has 2 electrons, neon has 2 and 8 electrons, argon has 2, 8 and 8 electrons, and so on. That full outer shell makes them all extremely unreactive. But just like the alkali metals and the halogens, their properties do change as you move down the group.
Take the noble gases. There's not much chemistry to see, but there are changes in their physical properties, for instance in their density. A balloon filled with helium rises quickly. A neon-filled balloon rises slowly. An argon balloon falls slowly. Krypton is denser still, and xenon is the densest of all.
In this case, the density of each noble gas increases as you move down the group from one gas to another. Quite often, properties like boiling points and melting points change progressively as you move down a group of elements. Now, how do things change along a horizontal period? This clip shows how fluorine reacts as you go along the period from sodium to sulfur.
This is fluorine and sodium. The reaction's fairly lively. So is the reaction between magnesium and fluorine. And now aluminium powder and fluorine. This is silicon and fluorine. This is phosphorus and fluorine. And this is sulfur. It may not look it, but there is a pattern. A pattern in the formula of the compounds. In the case of sodium, one sodium atom combines with one fluorine atom. For magnesium, one atom combines with 2 of fluorine. For aluminium, it's 1 and 3. And so a pattern emerges.
But why do the elements react in this way? Sodium in group 1 has 1 free electron in its outer shell, so it combines with 1 atom of fluorine. Magnesium in group 2 has 2 free electrons in its outer shell, so it combines with 2 atoms of fluorine. And so on. Another interesting part of the periodic table is the large area between the 2 extreme sides. They are called transition metals. Their properties change as you move across the table.
The long skinny bit in the middle of the periodic kingdom, which, well, chemists don't call it the long skinny bit, they call it the transition metals, is really interesting because in a sense it captures the progress of civilization. If you start on the far right, copper and zinc were the metals that were used for the Bronze Age. And as you gradually walk your way towards the left, you come to iron, which of course was the later Iron Age. If you go further across still, you get to elements like titanium. And of course, titanium is the material that makes space travel possible, light and strong and durable.
The clip explained that these transition metals were first isolated and made use of from right to left along this period. This is because each metal is more reactive than the next, so each one was more difficult to isolate from other compounds they react with. So to summarise, it's really important for your exam to know why the periodic table is arranged the way it is, especially why the elements are arranged in groups, how the group 1 alkali metals react and why, the group 7 halogens and their reactions, and the properties of the group 8, sometimes called group 0, noble gases. Here are some questions about the periodic table. Identify an element in the periodic table that has 2 electrons in its outer shell. Any element in group 2 has 2 electrons in its outer shell, so you could have said beryllium, magnesium, calcium, etc. Identify an element which combines with hydrogen to form a colourless acidic gas. Any element in group 7 reacts with hydrogen to form hydrogen halides, which are gases which dissolve in water to make acids. So you could have said chlorine, which reacts with hydrogen to form acidic hydrogen chloride gas, or fluorine, bromine, iodine, etc. Identify a group 7 halogen that will react with an aqueous solution of sodium bromide. The halogens become more reactive as you go up group 7, and a more reactive halogen will displace a less reactive one from a solution of its salt. So we're looking for a halogen that's higher up the group than bromine, that's either chlorine or fluorine. Find an element that forms ions with a double negative charge. Non-metals form ions by gaining electrons. Metals form ions by losing electrons. Metal ions in groups 1 to 3 have the same positive charge as their group number. Non-metal ions in groups 5 to 7 have the same negative charge as their group number, -8. Therefore, any group 6 element has 6 minus 8, that's -2 ions. Which noble gas in this periodic table has the lowest boiling point? For the noble gases in group 8, the boiling point increases as the size of the atoms increases. Helium, at the top of the group, has the smallest atom, with one shell with 2 electrons. So helium must have the lowest boiling point. Finally, select an element that will react more vigorously at room temperature with chlorine than sodium does. Sodium is an alkaline metal in group 1. The further an element is down group 1, the more vigorous is its reaction with chlorine. Potassium is further down group 1 than sodium, and so it will react more vigorously, as will rubidium, cesium, and so on. That's the end of the section on the periodic table. This section is about chemical reactions. You can tell a chemical reaction has taken place if one or more of the following things happen. There's a colour change, there's a temperature change, or a gas is given off, indicated by bubbling, fizzing, or a flame. Something new is always formed as a result of a chemical reaction. We'll look at several different types of chemical reactions. Combustion, redox reactions, that's reduction and oxidation, decomposition, displacement, and neutralization. First, combustion, commonly known as burning. When natural methane gas is burned in a furnace, how do we know that a chemical reaction is taking place? What ingredients are needed for combustion to take place? What is the chemical equation for the burning process? This next clip will help you.
The flame is basically a chemical reaction between the air and the gas. It produces lots of heat and light and also waste gases.
To understand what's really going on in here, you need to get right inside the flame. Fire is a chemical reaction. The flame you see is what comes out of this chemical reaction. Gas is so hot that they're glowing. The chemical reaction happened between fuel, natural gas, and oxygen from the air. But to get the reaction going, it also took heat energy. These are the 3 things you need for fire: a fuel, oxygen, and heat energy. The chemical reaction produces more heat, energy which is useful. But useful not just to us, it also keeps this reaction going, so long as the fuel and oxygen keep on coming.
One of the jobs I have to do whilst I'm on shift is to take measurements inside the furnace. This involves removing a block from the side of the furnace and poking a probe in there. The probe sucks the sample from the furnace, sends it down a tube to an analyzer, which will tell us exactly what goes on inside the whole furnace chamber. We're trying to reduce the amount of pollution to the environment and also to increase the amount of heat energy that we produce and make the most of this energy.
Let's go through the questions one by one. How do we know that a chemical reaction is taking place? A chemical reaction is taking place because something new is formed, another gas which goes up the chimney, and there's a large temperature change as heat is produced. Next question. What ingredients are needed for combustion to take place? The 3 ingredients that are essential to produce a fire are fuel, in this case methane gas, oxygen, and heat energy. If any one of these is missing, then the fire goes out. Changing the amounts of any of them changes the rate of combustion. And finally, what is the chemical equation for the burning process? The word equation for the burning of natural methane gas is methane plus oxygen produces carbon dioxide gas plus water. The chemical equation for that is CH4 plus 2O2 gives CO2 plus 2H2O. This burning reaction gives out a lot of heat. It's an exothermic reaction. Here's some more about the fire triangle, filmed after the Gulf War in the burning oil wells of Kuwait.
All fires can be extinguished by applying some simple scientific ideas.
You have three things. You have the heat, you have the source, and you have the oxygen. You eliminate one of those three and you can put a fire out.
Scientifically, it's very easy. Take away any one of these three ingredients and the fire goes out. But in practice, how do you stop the fuel from gushing out of a blown-up oil well? The obvious way is to block it off. These trucks are carrying a type of chemical mud which has to be pumped down the well.
Here we have some of the stingers that are used. The stinging method involves poking one of these mandrels down into the well so that you can pump mud into the well. The mud will overcome the pressure of the well, and when you get enough mud in the well, then the well is dead. This goes on to an end of a boom called an Athey wagon boom. And it's a long extension that will carry the pipe that carries the mud down to the stinger that goes into the well. So the Athey wagon has got a lot of weight. The end of this wagon has got enough weight to hold down the stinger to make sure that it stays in place once it enters the well.
With the well blocked, the fuel side of the fire triangle has been broken and the fire extinguished. But some fires can't be blocked off in this way. So what are the other options? The heat from the fire can be removed, breaking the fire triangle in a different place, and that's often done with water.
We're going to be using the water first of all, and that'll just essentially cool the oil. At the combustion point, you can just see a small area where the oil is leaving the wellbore, and there's a couple of feet there before it starts to burn. Now at that area where it starts to burn, the combustion area, if we start at that point with our water, it will cool the oil and we should be able to chase it right up, thus extinguishing the fire.
The third way of breaking the fire triangle is to remove the oxygen from the fire. Explosives use up all the oxygen around the fire, and that does the job. Alternatively, a dry powder can be used to smother the flames.
And we'll bring the dry chemical in with the cat, and which we'll set approximately about 8 feet away from the well, and the dry chemical will extinguish onto the fire, which the dry chemical will do is take away the oxygen and snuff it out. It will just automatically put her out, hopefully.
In this case, they're using dry powder and water, tackling the fire triangle from two sides.
The next type of chemical reactions are called redox reactions. That's reduction and oxidation. These next clips start by showing some oxidation taking place, and then go on to explain oxidation and reduction in two different ways.
The shiny surface of aluminium isn't quite what it seems. It's not pure metal. The outermost surface is actually a coat of aluminium oxide. It's a layer just a few atoms thick, so thin that you can see the shiny metal underneath. Whenever a bit of the oxide layer gets scratched off, it reforms very quickly, and that stops the aluminium reacting further. This is why aluminium foil is so good for wrapping food. The oxide layer stops the aluminium reacting with the chemicals in the food. But take the oxide layer away with a kind of chemical polish like this, and kitchen foil comes to life. This is what happens when naked aluminium meets oxygen in the air. The reaction makes so much heat that steam forms near the surface. Still, shiny aluminium is secretly rather reactive once its oxide layer has gone. And if you grind it up very finely, it will even burn. It almost explodes. Heat from the Bunsen burner makes the aluminium react with oxygen in the air, and a spectacular chain reaction begins. The white smoke that's left behind is aluminium oxide.
All burning reactions are examples of oxidation because the substance that's burnt is oxidized. Burning substances are chemically combining with oxygen. The oxygen is an oxidizing agent. But the oxidizing agent doesn't always have to be oxygen gas. Potassium chlorate is a strong oxidizing agent. It's got lots of oxygen in it. You'll see the point of the coin later. The white substance is the potassium chlorate. Phosphorus dissolved in a liquid is added. When it's touched with a hot metal rod, during the flash, the phosphorus was oxidized by the potassium chlorate. The reaction was so ferocious, it was as if the metal plate had been hit by a sledgehammer. Reactive metals like magnesium can even burn in carbon dioxide, a gas which normally puts out fires. The magnesium combines with oxygen in carbon dioxide, coating the jar with magnesium oxide powder. The black specks at the bottom are carbon.
Combustion is one form of oxidation. Rusting is another form of oxidation.
This is wire wool. It's made of iron. The water in this jar has been boiled, so it shouldn't contain much oxygen. But the water in this one is straight out of the tap. An hour later, the iron in the jar with the boiled water hasn't changed. But the rusty red of iron oxide is clear in this jar. Dissolved oxygen has combined with the iron, so we say it's been oxidized. That's true, but it's only one way of looking at it. Look much closer, and you realize that oxidation doesn't center on the oxygen at all. Oxidation is really all about the movement of electrons. This represents the surface of a piece of iron. The iron atoms are organized in a regular pattern called a lattice. Between the atoms, a sea of negatively charged electrons flows freely. When the iron meets water containing oxygen, the conditions are ripe for rusting to take place, because the water and the oxygen together attack the iron. Electrons leave the iron and move towards the oxygen, leaving the iron positively charged. With the help of the water, the oxygen molecules split up and absorb the negative electrons from the iron. They become negatively charged themselves. Remember, the iron is positive, so the opposite charges are attracted to each other and combine to form rust. The iron has combined with oxygen, but it's lost electrons. Here's one way to remember that. Oxidation is loss of electrons. Reduction is the exact opposite. The black powder is carbon, and the light-coloured powder is lead oxide. The lead is locked into the lead oxide, and heat alone won't split them apart. But add carbon, and that changes everything. As the mixture gets hot, 2 lead oxide particles react with 1 carbon atom. Oxygen leaves the lead oxide and transfers to the carbon. That makes carbon dioxide gas. It's invisible and just escapes into the air. But these tiny drops of lead get left behind. They've lost the oxygen they were paired with. So one way of understanding reduction is to say that it's loss of oxygen. But there's another way of looking at reduction, as a movement of electrons. The reason that lead and oxygen stick together in lead oxide is because they have opposite electric charges. The lead ions are positively charged and the oxygen ions are negative. Lead oxide is an ionic compound. But carbon doesn't like to form ionic bonds. Carbon and oxygen will only join together to make carbon dioxide with covalent bonds. So before the oxygen can join with the carbon, it has to get rid of its extra negative charge. The oxygen must give electrons to the lead. The lead ions gain electrons. That neutralizes their charge and turns them into lead atoms. It turns out that whenever something gets reduced, it gains electrons. So chemists actually define reduction that way. They say, if oxidation is loss, reduction is gain of electrons.
So oxidation is gaining oxygen or losing electrons. Reduction is the opposite, losing oxygen or gaining electrons. Remember oil rig. Oxidation is loss, reduction is gain of electrons. These are called redox reactions because they're a combination of reduction and oxidation. When lead oxide is reduced by carbon, it gives lead and carbon dioxide. The lead oxide is reduced to metallic lead, while the carbon is oxidized to carbon dioxide. The next chemical reaction to look at is decomposition. Decomposition is where a substance decomposes or breaks down. There are three types of decomposition. In thermal decomposition, a substance is broken down by heat. In electrolytic decomposition, a substance is broken down by an electric current. In catalytic decomposition, a substance is broken down by a catalyst. Both thermal and electrolytic decomposition are used to extract aluminium from aluminium oxide.
First, the electric current heats the aluminium oxide. Heating breaks the strong bonds between aluminium and oxygen. That leaves positive aluminium ions and negative oxygen ions floating in the mix. Next, electric charge draws the ions apart and neutralizes them, turning them into aluminium metal and oxygen gas.
So the heating process first decomposes aluminium oxide into aluminium and oxide ions. Then the electrolysis separates the ions and turns them into atoms of aluminium metal and oxygen gas. The presence of a catalyst can trigger a decomposition reaction. Decomposition using a catalyst can remove nitrous oxide gas from car exhaust emissions. In the presence of a catalyst, nitrous oxide decomposes into safe nitrogen and oxygen gases. Next, displacement reactions. In a displacement reaction, part of a compound is displaced during a chemical reaction. For example, a more reactive metal will displace a less reactive metal from its compounds. For example, copper oxide plus iron gives iron oxide plus copper. The iron displaces the copper from the copper oxide and takes the oxide over for itself. That's because iron is more reactive than copper. Iron oxide plus copper produces no reaction because the copper is less reactive than the iron. But how do you know which metal will displace another? It all depends on their position in the periodic table and where they are in the reactivity series. Potassium, sodium, calcium and magnesium burn easily in air and react with water with decreasing reactivity. Aluminium, zinc, iron, lead, copper and mercury oxidize in air. while silver and gold do not react with oxygen, water or dilute acids. It's useful to know the order of the metals in the reactivity series to help you answer questions about displacement reactions. You can probably think of some memorable sentences made from their chemical symbols, like kings naturally catch magnolias, and so on. And neutralization is another kind of chemical reaction you need to know about. Neutralization is the reaction between acids and alkalis. Let's remind ourselves what we mean by acid and alkali and how it's measured.
If I put universal indicator in orange juice, it turns slightly red. But if I put it into lemon juice, it turns very red. And this means the lemon juice is more acidic than orange juice. Now, if I try these experiments on lots of different substances, I end up with all these colours, from the very red at one end to the very blue at the other end.
If we number them from 1 for a strong acid to 14 for a strong alkali, with 7 in the middle meaning neutral, neither acid or alkali, then we have a scale, known as the pH scale. And the pH scale is how acidity and alkalinity are measured in scientific terms.
So the pH is a measure of whether a solution is acid, alkali or neutral. The pH scale goes from 1 to 14, from acid to alkaline. On the pH scale, 7 is neutral. All substances less than pH 7 are acid. All substances greater than pH 7 are alkaline.
If an acid reacts with an alkali, a number of things can happen depending on the two you're mixing together.
And one useful one is when you mix the right amount of acid, this one has a pH of 4, with the right amount of alkali, this has a pH of 11. The acid and the alkali neutralize each other.
An alkali neutralizes an acid to produce a salt. An alkali is a soluble base. Examples of bases are metal oxides, such as copper oxide, metal hydroxides, such as sodium hydroxide, and metal carbonates, such as calcium carbonate. Metal oxides neutralize acids to give a salt and water. For example, copper oxide plus sulfuric acid gives copper sulfate plus water. CuO plus H2SO4 gives CuSO4 plus H2O. That's base plus acid gives salt plus water. Combined in the correct proportions, the pH of the acid and alkali cancel each other out, and the pH of the resulting salt is neutral. That's why it's called a neutralization reaction. Two of the most common alkalis are sodium hydroxide and potassium hydroxide. They also react with acid to give us salt and water. Sodium hydroxide and hydrochloric acid give sodium chloride and water. NaOH plus HCl gives NaCl plus 2H2O. That's base plus acid gives salt plus water. Potassium hydroxide and nitric acid gives potassium nitrate plus water. KOH plus HNO3 gives KNO3 plus 2H2O. That's base plus acid gives salt plus water. Metal carbonates neutralize acids to give salt plus water plus carbon dioxide. For example, calcium carbonate and hydrochloric acid gives calcium chloride plus water plus carbon dioxide. CaCO3 plus 2HCl gives CaCl2 plus H2O plus CO2. That's base plus acid gives salt plus water plus carbon dioxide. Notice how neutralizing hydrochloric acid produces chlorides, neutralizing sulfuric acid produces sulfates, neutralizing nitric acid produces nitrates. There's more about chemical reactions in the higher tier science programme. That's it for chemical reactions. This section is about the rate of chemical reactions. There are many factors which increase or decrease the speed or rate of a chemical reaction. Watch the next clip and note down the factors that increase the speed of burning.
Fires need oxygen. The more oxygen, the faster they burn. With liquid oxygen, they burn faster still. This biscuit is soaked in liquid oxygen. A piece of wood burns so well when it's soaked in liquid oxygen that it even burns underwater. But what happens if you can't increase the amount of oxygen? Aluminium foil won't burn, but if you grind it into a fine powder and blow it into a flame, it will. Lumpy custard? Powdered custard? Most substances, like hydrogen in this jar, need a flame to burn. Or do they? This is platinum, used as a catalyst. This can is filled with natural gas. As the gas burns off the top, it's replaced by air coming in through the bottom, which mixes with the rest of the gas.
The ways shown in the clip to speed up burning were to increase the amount of oxygen getting to the fuel, or to increase the surface area of the fuel by breaking it into smaller pieces or a fine powder, or to add a catalyst like platinum. Another way of speeding up a chemical reaction is to increase the temperature. Rates of reaction can be explained using the collision theory. Particles of the reacting substances must collide before a reaction can take place. The more collisions, the faster the reaction. Here's a question about the collision theory. How can the four ways of speeding up a combustion reaction be explained by using the collision theory? A higher concentration of reactants, fuel or oxygen, means that there are more particles involved, so there's more chance of them colliding and reacting. A larger surface area of fuel means more particles are exposed to oxygen, so there's more chance of them colliding and reacting. A higher temperature excites particles into moving more quickly, so there's more chance of them colliding and reacting. Adding a catalyst lowers the amount of energy needed for colliding particles to successfully react. That's it for rates of reactions. This section looks at the energy transfers in reactions. Most chemical reactions become hotter or colder as they proceed. They either give out or absorb heat. Reactions that give out heat are called exothermic reactions. Reactions that take in or absorb heat are called endothermic reactions. This clip looks at some exothermic reactions.
This is a strip of magnesium metal. Drop it into hydrochloric acid and watch using a heat-sensitive camera. Blue is cold, purple is warm, yellow is hot, white is even hotter. Clearly the reaction releases heat. It's exothermic. You don't even need solid chemicals for an exothermic reaction. The water in this beaker is at room temperature, but add another cold, clear liquid and a bubbling reaction starts immediately. The heat-sensitive camera reveals gas being given off. It shows up because it's hot. The heat seems to come from nowhere, but actually it was locked up in the chemicals all along.
There's a very exothermic reaction called a thermit reaction. This creates a vast amount of heat, and has some useful practical applications.
The grey powder is aluminium. The rusty red powder is iron oxide. We put the mixture into a ceramic pot to withstand the intense heat. A thin strip of magnesium acts as a fuse. The reaction is highly exothermic. It clearly releases a huge amount of heat. What you can't see is why. What's happening inside the reaction. At room temperature, aluminium and iron oxide don't react. It takes the heat from something like burning magnesium to get them going. After that, the magnesium isn't really part of the show. The fireworks happen through this reaction, because aluminium and oxygen are both such reactive elements, and they're desperate to get together. Metal aluminium goes in, and it comes out oxidized. But the iron oxide that goes in comes out reduced. You could say that the oxygen has swapped partners. It's gone off with the aluminium and dumped the iron. Here's the proof. At the bottom of the ceramic pot, we made a hole, so whatever is left behind by the thermit reaction would drip down into this sand-filled bucket. It's iron metal. Because the thermit reaction combines both reduction and oxidation, it's called a redox reaction.
The thermit reaction is a redox reaction, a combination of reduction and oxidation. While the aluminium is oxidized to aluminium oxide, the iron oxide is reduced to metallic iron. The reaction also releases a huge amount of heat, which melts the iron. The thermit process can be used to weld railway lines and other metals. An endothermic reaction is the opposite of an exothermic reaction. It absorbs heat, like in this instant ice pack.
Inside the pack are dry ammonium nitrate crystals and a small bag of water. Break the bag open and the reaction starts. The heat-sensitive camera shows the water as yellow. It's quite warm. Black shows where the mixture is much colder, as the endothermic reaction between ammonium nitrate and water takes heat out of the beaker. Quickly, it's down to just 5 Celsius, as cold as a fridge.
So, in an endothermic reaction, heat is taken in from the surroundings to create the cooling effect. There's more about energy transfers in reactions in the higher tier science programme. That's the end of the whole section on patterns of chemical behaviour. That's the end of this foundation chemistry programme. There are other programmes about biology and physics, which all help towards grade C. And there's a higher tier science programme for those who want to aim higher. And don't forget, there's also the GCSE Bitesize books and the GCSE Bitesize website.